Is this on?
That's a polymer almanac. Right.
Kent, is this on?
It's on.
I don't see the light. Okay.
I love those videos from the stereo, satellites that are out there. They're just spectacular.
Oh, yeah.
All right.
Okay. And
Grab my water.
works. Okay.
Okay. Well, Kent is definitely a hard act to follow. Yeah. Is the left side? Okay. Okay. Well, good morning. I'm Tatjana Curcic, and today I will tell you about some exciting research that goes on in the atomic and molecular physics program. Generally speaking, the portfolio concerns itself with interactions, understanding interactions between atoms, molecules, ions, and photons of different kinds. And it can roughly be divided into two large areas, cold quantum gases and quantum information science, with these sub-research areas that are listed here. Today I'm going to talk about some recent results in the areas in blue. And here's the outline of my talk. I will give you a report on the recent developments in the ultracold molecules MURI, and then we're going to celebrate really two outstanding PIs on some very special occasions of wonderful awards. Okay, so let me start with the MURI. This is an FY09 MURI on ultracold molecules. It ends this summer, so this is the last time I'll be reporting to you on this MURI. There are two teams. These are the participating institutions in the MURI. And the reason we want to study ultracold molecules is it's well known that they give us a lot more possibilities than cold atoms in many different areas. And we're interested in exploring, maybe discovering novel phases of matter, doing some quantum information with cold molecules, and understanding chemistry, chemical reactions, and molecular collisions in an unprecedented way, really. And I will talk more about that. But because this is the last time you'll hear about this MURI, I thought it would be nice to point out some of the highlights from the past 4.5 years. As I've mentioned, this has been an extraordinarily successful MURI with over 200 publications, many of them in physical review letters, some Nature and Science, and so on. And part of the reason is that first of all, it's really, really outstanding people, but we were there, it's the timing as well. We were there at the right time, and back when we started the MURI, we were the biggest, by far the biggest supporter of this field. And also there was a huge breakthrough in 2008, summer of 2008, with potassium rubidium agila being generated in the ultracold regime. And after that, the field really exploded. So here's some of the highlights. I'm not going to have the time to go over all of them. But in 2009, for example, first ultracold chemistry experiment demonstrated quantum effects was done at GILA, and also full control of the ground state hyperfine states, which potassium rubidium has 36, was demonstrated. So that was really beautiful. And that was followed with a couple of years of lovely experiments at GILA with potassium, with this wonderful quantum ultracold gas, such as control of ultracold reaction rates using electric fields, molecular orientation, dimensionality. What they really want to do at GILA is not so much chemistry with potassium rubidium, but many body physics. So they wanted to suppress those reactions. So they put potassium rubidium in a 3D optical lattice and showed very long lifetimes. And I've talked about all of this last time I reported in the MURI 3 years ago. This is just a reminder. And by the way, they have very long lifetimes, and just recently, last fall, they had a really lovely paper realizing a lattice spin model with potassium rubidium, so a lattice spin model with dipolar interaction observation of dipolar exchange interaction. I'm not going to talk about it this year. And then in 2010, there was that spectacular result of first laser cooling of a molecule. This was done at Yale, strontium fluoride, and I talked about that as well 3 years ago. And in 2012, there was a sort of another turning point in the field with another spectacular result, first evaporative cooling of a molecule, and it was OH. Now, evaporative cooling is for cold atoms. It's the last step after laser cooling, the last step that gets you to ultra-cold state, like Bose-Einstein condensate. So the fact that this was shown to work with a molecule was really, really important, and it was OH. It was a chemically interesting molecule. And this really opened up possibilities for investigating molecular collisions and chemistry in the quantum regime. But I'll say more about that. And then from the past year, again, there was a number of very, very nice results, and I'll focus on these three here. So I showed pretty much this slide or this result 3 years ago. This is done at Yale in Dave DeMille's group. This was the first laser cooling of a molecule, which was really thought to be almost impossible prior to this. And just very quickly, he uses a cryogenic source, buffer gas cooling. Here's a little picture. Here's the slowing region with the cooling laser, probing region. And here's a clear signature of Doppler cooling where the velocity distribution is narrowed, and they even observed sub-Doppler cooling, Sisyphus cooling, and this was done in one dimension. This was in one transverse direction of the beam. The latest in November is the first 3D MOT of a molecule. MOT is magneto-optical trapping. That's a workhorse for cold atoms. And this is a really, really big deal. So they've basically managed to cool strontium fluoride in all three directions and trap. And here's a beautiful picture of a cloud of this is trying to do. We're trying to cool and trap so that then we can maybe cool further, but do interesting science, whether it's many-body physics, quantum information, chemistry, what have you. And this is the first example of a 3D MOT of a molecule not published yet. So that's wonderful. Okay, moving on. John Doyle at Harvard has been working for years now, since before the Muri, on buffer cooling techniques. And just very briefly, what it is, it's basically what the name says. You are cooling your species of interest through thermalization with a cryogenic gas, typically helium, via collisions, of course. And what's nice about it, you can get as low as 300 millikelvin this way if you use helium-3. And what's nice about it is it's very, very general. So it works for any atoms or molecules, okay? And the molecules typically come out of this buffer gas cooling cell at about 150 meters per second velocities. Now, I just said that what we want to do in order to be able to do interesting science in the quantum regime is to trap and cool the sample to the quantum regime. And 150 meters per second is a little too fast to be able to do that. And so John's been working for years, since the beginning of the Muri, on this particular problem, and they just, this paper has been accepted to physical review letters. And they've just managed to do that with calcium fluoride. They had to develop a two-stage buffer gas cooling cell. So now the molecules come out at 30 meters per second instead of 150. And they've implemented here magnetical slowing and a two-stage optical pumping technique. And voila, they've trapped. This is a spectrum of trapped calcium fluoride molecules at different times. That gives you lifetime of the trap of about half a second, which is nice. But this is really exciting. So we have now another completely different method from the previous one by which we can cool and trap molecules that we can then do interesting things with. But in this case, what's particularly exciting is that it's a general technique and should be applicable to magnetically, chemically diverse molecules, including polyatomic molecules. So very, very exciting. In Heather Lewandowski's group, Agila, she is working with CH, okay? Now here's another chemically interesting molecule. She's also working with Stark deceleration. She's been doing that for years. That's a well-established technique, yet another different technique for slowing molecules, and here's her Stark decelerator. But what she's doing now that's new and different is that she's combining buffer gas cooling that John Doyle has developed, really, the technique, with Stark decelerator. And they've already shown the preliminary results written up here show that they have a very intense CH beam coming out of the buffer using this buffer gas cooling technique. In fact, 2 times 10 to the 11 CH molecules per pulse, all in the same ground state. So this is really exciting, and they've done very detailed calculations of coupling this source to the Stark decelerator, and then calculating what they can expect to get, and the numbers look really, really wonderful. So I can't wait really to see in the near future CH molecules, which are important for many things like combustion and combustion reactions, being trapped and then doing detailed chemistry with those. And just for completeness, I did show this slide last year, but it's again, it fits the story here very well. The spectacular result of evaporative cooling of OH from a year and a half ago, 2012. So now here we have OH, we can do evaporative cooling, we have CH, we have a couple of methods that have shown to work well for trapping, cooling and trapping, and we really are ready to move on to a new era in cold molecules, particularly for the applications of molecular collisions and cold chemistry or quantum chemistry, and investigating chemistry with an unprecedented detail, really, and resolution. So that's where we're going in the future. My colleague Mike Berman and I have excited about. Okay. So now, I'd like to tell you about Anna Maria Ray. Dr. Roach has already mentioned her on the occasion of her receiving the latest MacArthur Genius Award. It turns out she's received this past year several prestigious awards, including the PCASE award. She was nominated by the Department of Commerce. She's a NIST employee. And also the 2014 Maria Geppert-Meyer Award that's given, it's an APS reward given to an outstanding woman physicist. Anna Maria is one of my younger PIs. She's a theorist. I'm not going to show any equations, but she works very, very closely with experimentalists, as I hope to convey. And rather than talking matter, just like much of my portfolio is focused applications, more than that, more than precision measurement and sensing. by Richard Feynman more than 30 years ago, when he postulated that someday we would be simulating one quantum system with another, because that'll be really the only way to understand the quantum system of interest. And that's indeed what we try to do with atomic simulators or quantum simulators. So the poster child example of a complex quantum system of interest is high-tissue superconductors, for example, which were discovered more than 25 years ago, and we still don't understand how they work. And we want to simulate such complex materials with atoms, cold atoms, and molecules in optical lattices, where the role of electrons, which of course determine the properties, their behaviors determine the properties in the real materials, is taken on by atoms or molecules, and the crystal lattice is replaced by an optical lattice, which is a standing laser wave. There are two important and big differences between our quantum atomic simulator and real materials. And that is that atoms are a lot heavier than electrons, as you know, and optical lattice spacing is much larger than angstrom-sized crystal lattice spacing. And these two important differences unfortunately lead to a very quite unpleasant requirement for extremely low temperatures. For these atomic simulators, if we want to be in the quantum regime that the materials of interest are in, that we want to understand better, and in fact what corresponds to Kelvin temperature in solid state systems is in the picokelvin range for in atomic systems. So that's hard. Researchers are routinely generating cold atoms in the nanokelvin regime, and we're pushing the picokelvin frontier, but we're not there yet. So what can we do to get there and to get to the point where we can do these successful simulations? Well, for one thing, we can develop sophisticated cooling methods, which a lot of people are working on. And a couple of years ago, when I talked about another Muri, quantum simulation Muri, I talked about Marcus Greiner's nice work with his famous quantum gas microscope and his new algorithmic cooling technique. So that's one example of that. We can explore new types of systems beyond alkali atoms, which are the examples of these new types of systems. And by the way, in my portfolio, we do all of them with the exception of trapped ions for quantum simulation. And we can also take advantage of ultra-precise tools like clocks that work in all of these new types of systems, and the work that we support is primarily, and much of her work is focused on alkaline earth atoms. So let me just tell you very quickly what why alkaline earth atoms are interesting. And they are very, very interesting. First of all, they sit in their group 2 atoms here and here. As well as these two. And here's an artist's rendition of one of them, of strontium. Basically, they have a closed shell, S shell, with 2 electrons with opposite spins in it. And as a result of that, they have there are 2 interesting properties of these atoms that, which is why they're popular with cold in atomic physics these days. One is that that they have they have 2 electrons, so they have a singlet and triplet states, and we're going to concern ourselves just with the spin 0 triplet state. And this transition is typically in the optical region. Here for strontium it's 698 nanometers, but this triplet state is a very long-lived metastable state with a very narrow line width in millihertz. So what you have here is a very narrow line width state, excited state in an optical transition. So of course, immediately you think delta F over F is going to be very small, so it's a great candidate for precision measurements like for clocks. And it sure is. In fact, the best clock today is it's the so-called optical lattice clock, and it uses alkaline earth atoms, okay? As of best clock as a few months ago. But another interesting property of alkaline earth atoms that I want to emphasize here is so the two electrons are with opposite spins, so the electronic spin is 0. They're in the s orbital. The angular orbital momentum is 0. So the total electronic angular momentum J is 0. The fermionic isotopes of these have a non-zero nuclear spin, as high as 5/2. So there's only nuclear spin, and J dot I being the nuclear spin, is 0. So hyperfine interaction is 0. So what you have is the ground state has these hyperfine, basically all the hyperfine states due to the nuclear spin are degenerate. So you have SUN symmetry where n is 2I plus 1. So it can be up to 10 for 5/2 spin. I know this is a lot of information, but this is all to say that that we are not tied now. We have something new to explore here, because normally in normal materials you have electrons spin 1/2. You have SU symmetry, okay? I'm sorry, SU2 symmetry. Here we have a chance to explore something very new and different, and this is Anna Maria was one of the first people to start exploring this in terms of maybe novel phases of matter that nature doesn't give us, because we don't have materials with SUN symmetry. And let me, this is a good segue to her accomplishments that I want to emphasize over the past few years. One is that she and her co-workers a couple of years ago came up with a new cooling methods. This is back to the cooling, the picokelvin challenge, if you wish. And this is utilizing the SUN symmetry in these alkaline earth atoms. So it's not just a theoretical curiosity. But what's most beautiful about this is that this effective cooling methods where they predicted you can get colder than by utilizing this nuclear spin and SUN symmetry was experimentally confirmed in an experiment in Japan in Takahashi's group in Kyoto. So it really works. I mentioned the best clock in the world, which is now strontium and ytterbium clocks, one at Gila, one at NIST, both in Boulder. And Anna Maria's theoretical insight played a really critical role in the development of this clock, the strontium one at Gila. One of the major sources of error was frequency shifts due to collisions of strontium atoms, and they really didn't know how to get around it. So they asked Anna Maria for help a couple of years ago, and it was her detailed and new understanding of interactions that guided the experiments in a very counterintuitive direction, by the way, and led to the development of the best clock that was just published in January. And by the way, we did not support let me just make it clear, the experimental development of the clock. That was supported by other agencies, but it's her theoretical insights and guidance that was critical for that. And most recently, and to me, I'm probably most excited about this, is that she's basically realized that she can take advantage of these high precision tools like the strontium clock, which is depicted here, and realize these many-body physics models and quantum magnetism in the clock, which is at microkelvin temperature, far from picokelvin. And sure enough, there was a science paper, a very nice science paper this fall, where they showed exactly that realization of quantum magnetism. This is with in a nuclear spin polarized samples, so the nuclear spin degree of freedom was frozen. And what she tells me just now the other day is that they have first measurements of when they relax that nuclear spin degree of freedom. So they have first measurements of SUN quantum magnetism in clocks, and this is of course leading towards discovery of novel phases of matter and whatnot. So this is really wonderful and big, and she is a true out-of-the-box thinker. If you look at all of these things that I hopefully conveyed that to you. Okay. Oh, and she has graciously accepted our invitation to give a colloquium here at AFOSR, which will be on the 29th of May, so mark your calendars. All right, now I have 10 minutes or so to talk about 50 years of Steve Harris's accomplishments. Professor Harris, his last grant with us ended this past September, and it marked full, continuous 50 years of funding from U.S. Air Force. And it's been an incredible 50 years, and Howie already mentioned some of that. So of course there's no way to do justice for this, but I will try anyway. So I solicited Howie's help particularly with the early years. Oh, and by the way, Howie also told me that when he first came to Hanscom, which was how he started with the Air Force before AFOSR, this was in 1968. His first grant was or contract at the time was with Steve Harris, so I thought that was interesting too. Back at this time in 1968, pulsed optical parametric oscillators were being worked on at places like Bell Labs, and Steve decided that he wanted to make a CW OPO. And he and his student at the time, Bob Beyer, did just that. They made the first CW OPO in 1968. And as Howie already mentioned in his talk, these OPOs, mid-infrared OPOs, are now on all large Air Force aircraft, and they've proved extremely effective and successful in spoofing heat-seeking missiles. This technology, two things I want to note about this is that this technology took a couple of decades to develop, to move from the lab onto an aircraft. Of course, I think the technology that was developed in the 80s, maybe. So it does take decades to move it to a very, very, very useful application in this case. But another thing is, I was talking to Howie the other day, and he mentioned that when Bob Beyer was on a scientific advisory board here a few years ago, they were chatting, and Bob made a comment. They were talking about these early years, and Bob made a comment, and I'm paraphrasing. Who would have imagined back then that you could put an OPO on an airplane and do such useful things with it? And I think that's a really interesting comment. Not only when people do basic research, not only that they can't always, most of the time they can't see the applications that the science will end up supporting. I mean, there are many examples of that. Take transistor, for example. But oftentimes they can't even imagine that this thing can end up on an airplane and be so useful. So anyway, it's an important thing to keep in mind, I think, about basic research. Okay, in the interest of time, I'm going to skip over this and talk a little bit about EIT and slow light, and then more recent work from Steve Harris. Of course, slow light, one can talk for an hour about just that, and I decided to cram it all onto one slide. So just as a reminder, electromagnetically induced transparency is a phenomenon where if you have an atomic medium and you shine light on resonance to transition in that atomic vapor or medium, light will get absorbed, the medium will be opaque. However, if you couple another level to those two, it turns out that the medium will turn transparent, and that's the electromagnetically induced transparency phenomenon. It's a quantum interference phenomenon. It was first predicted by a Russian group in the mid-80s. And of course, this is playing with the dispersion of the medium and the index of refraction, which is here in blue, which all has to do, of course, with the light propagation, affects propagation of observed by Steve Harris and his coworkers in 1991. And this is now transmission, not absorption. And you see zero transmission at on resonance, right? And then when you turn the coupling laser on, you see the characteristic peak. So that was the first demonstration of EIT, which was followed in 95 by first demonstration of optical pulse delay using EIT. Okay, this is now slow light, except that they didn't, I believe, call it slow light back then. We're talking about a couple tens of nanosecond delays. And then there was that famous and spectacular paper from 1999, the slow light paper. And this is collaboration between Lena Howe and Steve Harris, where they had now used, this was all done in warm strontium vapor, and now they used ultra-cold gas, okay? I think it was rubidium, but that's not important. But they used ultra-cold gas, and they realized they measured 7 microsecond pulse delays and light moving at bicycle speeds, okay, as you can see here. This caused an explosion of interest in this phenomenon of EIT. By the way, EIT is just one of several mechanisms for playing with the dispersion of the medium and slowing light, but I'm not going to talk about the other mechanisms. I'm talking about Steve Harris here. So this really caused an explosion of interest, both scientific and technological. There are some very obvious applications in telecommunications, optical pulse delays, optical buffers. Shortly after this, they showed stopped light as well. And that's obviously important for quantum memory. But I just want to point out that the phenomenon of EIT is so ubiquitous today. And this is only 20 years later, right? So ubiquitous in so much research. Certainly in my field. And I gave one example here of something that I presented at the spring review last year. Okay, I really have to hurry up here. It's making its way onto chip scale technologies as well, and as Howie pointed out, they were predicted to, by Thomson Reuters, because of the huge impact, to win the Nobel Prize, and that was the year that we all know Dave Wineland and Serge Haroche won the Nobel Prize. Since then, Steve has, in the 2000s, he kind of shifted his attention more and focused on to single photons, quantum optics for quantum communication, secure communication applications. And I talked about this paper in my first spring review talk in 2008, where they modulated single photon wave packets. Here's an unmodulated wave packet, and here's modulated with this kind of signal. They could do any kind of signal, and unfortunately I don't have time to talk about this, but EIT is implemented here, is used here as well. And since then they've also done show that you can use spread spectrum technologies for single photons and hide successful single photons in a noisy environment. And in the last few years, decade or so, there were all these wonderful, intense, coherent X-ray sources, X-ray FELs around the world, several of them, and Steve really wanted to do nonlinear optics with those. There's one at Stanford. He couldn't get time on it, so they went to Japan. And again, with careful, the diamond is the nonlinear medium here, with careful phase matching and background radiation considerations, they did observe second harmonic generation with X-rays here. And I really mentioned this example because Steve retired officially last March. This paper was written up, I don't think it's published yet, it was written up last summer, and he's staying at the cutting edge all along, okay? And I do want to spend 2 minutes on this summary slide. And in way of summary, let me point out 3 things here. Our Commander General Masiello visited us last month and talked about his priorities. His number 1 priority is the mission, of course. And he said that the most important thing about our mission is leading discovery. And this was music to my ears, because this is what we do here at AFOSR. But in order for us to do this well, for us program officers, we absolutely have to not just stay at, but stay ahead of the cutting edge in our respective research areas. And the most important factor in that is close interactions with the research community. And I'm talking conferences, workshops, site visits, professional society activities, all of that. Really, really important. Perhaps the Ultracold Molecules project is a good case in point. It was, honestly, there was about a decade of very slow progress in the field and very small funding. And it's not just luck that the field exploded, and that coincided with our MURI and the boost of funding, but also scientific breakthroughs that the field was ready for. You know, the big KRB breakthrough happened in the summer of 2008. I submitted the topic in the spring of 2008. I knew what was brewing at GILA, okay? Finding and supporting young talent. We do a very good job, I think, at AFOSR at this, and this is something that's one of our priorities, and I think it's really, really important. We have a nice YIP program. Finding young talent folds somewhat into my first point. Talking to students and postdocs, really, really important, because that's our future pool of our future PIs. I knew Anna Maria when she was a graduate student. And I started funding her. AFOSR grant was one of her first, if not her first grant, okay, when she went to Colorado. And I can't emphasize enough the importance of sustained funding to the best. And it's very important that we refresh our portfolios, that we don't let them go stale. That's very important. But it's just as important to be able to provide sustained funding to the best. And this is one of our biggest strengths, in my opinion. And not all funding agencies are able to do this either. And this is what I get also, what we get constantly, not just from our PIs, but from people that don't get our funding. They say that's really one of the strengths of AFOSR. And thank you for your attention.
We have time for questions.
Jim.
When you cool these molecules to below 1 Kelvin with the buffer gas cooling method and you trap them with magnetic field, don't they form condensed states?
No.
How do you extract them out as a beam?
Repeat the question.
Okay, the question is, when you cool them when you cool molecules with buffer gas cooling, don't they condense, and how do you extract them as a beam? Yeah, they don't condense. First of all, it's a very dilute gas typically, and I mean, we can talk more about it. And there are ways of extracting just those molecules, that molecular beam, and not separating it from the cryogenic cooler. But it's a fairly dilute gas. We can talk about that. Any other questions?